Hey everyone, Miss Basega here, and today we're learning about fission versus fusion. In this case, fission refers to when you have some sort of large, heavy element, one with a very high atomic mass, and that large, unstable nucleus breaks apart into two or more daughter nuclei. Now, unlike alpha or beta emission where that's putting forth a very specific particle, spontaneous fission would be when these nuclei break apart and make two or more random daughter nuclei of roughly the same size. Now, I said spontaneous. It turns out fission reactions can either be spontaneous, meaning they occur on their own, or catalyzed, meaning something starts that reaction. Some examples that we're going to go through today include spontaneously fissile nuclei, ones that are just big and unstable, so they split apart on their own. The Oklo mine in Gabon, Africa, and how current nuclear power plants work. So to start us off, let's talk about spontaneous fission. You'll notice that spontaneous fission occurs with nuclei that are very large, that have large atomic mass numbers, like this californium-252. It splits apart into two daughter nuclei, xenon, and I believe that's ruthenium, that are roughly the same size. It also emits 4 neutrons, and this Q here is a release of energy. And think about it like this. Each of these 6 particles, 1, 2, 3, 4, 5, 6, has to have kinetic energy, and that kinetic energy gets split between all of those pieces. A thing about spontaneous fission is it doesn't always occur perfectly predictably. So the same californium atom could also split apart into cesium, technetium, and 3 neutrons plus energy. But spontaneous fission can also occur in other places. So we're going to take a look at a spontaneous fission reactor.
In 1972, French scientists were testing some uranium taken from the Oklo mine in Gabon, Central Africa, when they noticed something odd. They had a lot less usable uranium than they thought they did. Enough uranium to make 6 nuclear bombs was just missing. Normally, the uranium found in ore comes in 3 different varieties, or isotopes, each with a different number of neutrons in its nuclei. Since their atomic makeups are slightly different, they all react in different ways. But when you're looking for the stuff that releases enough energy to light up a city or vaporize an island when you split it, the isotope you're looking for is uranium-235. Now, uranium ore should contain the same ratios of different isotopes no matter where it's found in the world. So the French scientists knew that in the ore they were studying, they were supposed to find a concentration of uranium-235 that was exactly 0.72%. But it turns out that they only had a concentration of 0.717%. That might not sound like a lot, but spread out over the giant mine at Oklo, it looked like 200 kilograms of uranium-235 had disappeared. After a few weeks of frantic investigation, the scientists realized that they were never going to find the missing uranium because it had been gone for 2 billion years. What they had discovered was the remains of an ancient natural nuclear reactor. Some physicists had theorized that certain kinds of nuclear reactors could exist naturally, but only under very specific conditions. And it turns out that the uranium deposits at the Oklo mine and the area around it fulfilled all of those conditions. Basically, a natural nuclear reactor needs the same ingredients that modern nuclear power plants do. You need an atom that you can split pretty quickly and easily, you need neutrons to do the splitting, and you need a way to control that reaction so once the atoms start breaking apart and releasing face-melting amounts of energy, you don't have a nuclear Armageddon on your hands. When the first ingredient, an atom of uranium-235, is struck by the second ingredient, a stray neutron, the atom becomes so unstable that it splits, releasing a ton of energy, plus a few more neutrons that fly off and split other uranium atoms, creating a chain reaction. And way back, a couple of billion years ago, Oklo had both of those ingredients. Back then, natural concentrations of uranium-235 pretty much everywhere on the planet were at a healthy 3%, which is about as much as nuclear power plants use in their fuel rods today. And in addition to all that potential fuel, Oklo also has lots of neutrons flying around just because over time, uranium-235 naturally decays into another element, an isotope of thorium, and in the process it releases a neutron. Now, in a natural, uncontrolled reaction, all of those those neutrons being released would be moving way too fast to split an atom. Instead of hitting another atom, they'd mostly just rocket away without hitting anything, and the reaction would simply stop. But this didn't happen at Oklo because the deposit also had the third major ingredient, a way to control the reaction. The Oklo deposit was full of water. Groundwater, to be precise, which continuously flowed into the site, slowing the neutrons down enough that they had time to hit other atoms of uranium-235 and keep the chain reaction going. Now, you'd think that with all these atoms getting split and energy being released, things would spin out of control pretty fast. But it turns out that the groundwater prevented that from happening as well. As more and more uranium split, the energy being released made the water hotter. After about half an hour of that, the water would get so hot that it would start to boil off. And without the groundwater to slow them down, the neutrons would start moving too fast to hit any more uranium, which would quickly stop the reaction. But eventually the water would come back and slow down the neutrons enough that the chain reaction would start over. And on this cycle went, likely for hundreds of thousands of years. All told, the deposits in the Oklo area probably had an average ongoing power output of about 100 kilowatts, which is enough to power about 100 washing machines for eons. But none of the energy was ever put to any use. Eventually, the reaction used up so much of the U-235 in the deposit that the concentration got too low and the reaction stopped. So the energy produced by Oklo's natural nuclear reactor quietly dissipated, leaving only that missing uranium and a few byproducts as evidence that it ever existed.